let's look at an example. Intermolecular forces are important because they give matter certain characteristics that allow them to either physically interact with each other or not. For example, vinegar is very easily mixable with water. The two are going to mix together and create, as we would observe, going back to a definition from chapter 1, a homogeneous mixture. Right, this may be vinegar mixed with water, but it all just looks clear and colorless. It all just looks the same. It all looks evenly mixed. There's no layering that's occurring. And we would assume or conclude that this is occurring because at the molecular level, vinegar and water can interact with each other in a very strong and attractive way. What we are going to do is illustrate the molecules and figure out what electrostatic intermolecular forces are possible. There may be more than one listed. In fact, there's going to be more than one listed. So I'm going to encourage you to draw out the structure for vinegar. If you're not exactly sure what this looks like, you can always look it up online and partner that with water and see in what ways you can configure these two molecules together and what kinds of intermolecular forces can you get as a result. All right, welcome back. Let's come together. We'll start by drawing vinegar. Again, if you're not sure what this looks like, you are totally free to look this up online. I am just going to illustrate my little vinegar down below. So we have a CH3, meaning that there's a carbon with 3 hydrogens coming off of it. COOH is going to be off of this first carbon, a little carbon right here, double bond to one of our oxygens, and then an OH, single bond to another, single bond to the oxygen after that. Now, this structure is definitely more complicated. As a disclaimer, like particularly if you're in my class and you're like, oh my gosh, we never talked about large structures like this, totally fine. They're going to be a little bit more apparent as we kind of get like general practice with them as we go. So if you had to look this up, no shame. I would never shame anyone for needing a little bit of extra information. All right, the vinegar molecule, our acetic acid, as it is drawn below though, we can kind of start picking out where there's going to be polar moments, non-polar moments, and that's going to tell us how this molecule will potentially interact with water. All right, so I'm going to switch colors for contrast. Contrast is becoming even more useful. So carbon to carbon is going to form a non-polar bond. Similarly, carbon to oxygen forms a non-polar bond. So we have an entire kind of non-polar half to this molecule, which is going to have some really important implications that we'll talk about in a little bit. Carbon to oxygen, as we discussed earlier with the case of carbon dioxide, does form a polar bond. So we're going to get a polar bond in this direction, a polar bond that does not perfectly cancel out in this direction, and similarly, oxygen to hydrogen is another very polar bond, so we have a polar moment in this direction. So we're going to end up with kind of 2 areas of partially negative charge here, a slight partially positive charge here, and definitely a partially positive on top of this carbon here. Now again, because nothing is like linearly distributed, in 3D space, we are not actually going to end up with any canceling of these negatives and positives. We're not going to have a case like carbon dioxide. Let's observe where the positives and negatives are. And we're going to start adding some water molecules around these locations. So the first kind of positive-negative dipole moment we can see here, there's going to be positivity left on the carbon, but it's kind of crowded in there. So let's add a hydrogen, oxygen-hydrogen combination right here. Right, so partially negative oxygen is going to attract a partially positive hydrogen. The next thing that we have to assess, since we do have a dipole-dipole moment, a dipole-dipole bond, dipole-dipole intermolecular force, which is what is right here with this dotted line, we have to ask ourselves, is this a hydrogen bond? Right, so we have one dipole-dipole interaction, but is this also a very special dipole-dipole? The way that we answer that question is by observing both of the bonds that are coming together that caused this dipole moment. The first is an OH, which is one of the requirements to form a hydrogen bond, right? We have great polarity here, a great charge distribution, great charge separation. Carbon-oxygen, though, does not qualify. The electronegativity difference between carbon and oxygen is not so great that we would expect to see a very, very strong dipole-dipole interaction. So for that reason, this intermolecular force with the water coming off of this double bonded oxygen is just going to be labeled as a dipole-dipole interaction. All right, the other polar moment that is down here, down below with our partially negative oxygen, the partially positive hydrogen, we can interact with another water molecule with a hydrogen coming in close contact with our partially negative oxygen. Oxygen here, hydrogen, partial negatives. So we can start to get some really nice stacked interactions where a hydrogen's going to attract an oxygen's going to attract a hydrogen. We're going to end up with two dipole-dipole bonds here if the molecules arrange themselves in the perfect way. Is this going to happen guaranteed? Maybe, maybe not, right? This is in a liquid state. So these molecules will be constantly moving past one another, right? That's what it means to be a liquid, is that these things are going to be slipping by one another. But the intermolecular forces as they form are going to be strong enough to keep this in a liquid state and prevent it from moving into a gaseous state, or prevent it from layering even. All right, so the interactions that form between this oxygen and hydrogen and this oxygen and hydrogen are going to be classified as a dipole bond, dipole intermolecular force. And now we can also ask ourselves that special question, does this count as the hydrogen bonding case? Well, we do have an oxygen and a hydrogen interacting with an oxygen and a hydrogen. I don't know why I said that so weird. Hydrogen. Since we do have OH bond interacting with OH bond at long distance along these dotted lines, we are also going to have a hydrogen bond. This dipole-dipole interaction is the special case where we are specifically working with a hydrogen bonding intermolecular force. Now, hydrogen bonds are, again, really strong dipole-dipole interactions. They're very, very stable. We can explain the homogeneous mixture forming between vinegar and water because of the strength of the individual intermolecular forces that are forming here, here, and here. And as the molecules slip past one another, we also have the chance to form another dipole-dipole interaction kind of here. This water can move around and still interact with this oxygen here, right? There are plenty of locations as the molecules slip by one another where we are going to form stable interactions.